All right, welcome to lesson 2 of our first unit in grade 12 pre-cal. So we're still going to be looking at angles in standard position, but we're going to be adding a different unit that you've never probably seen before. And we're also going to be talking about how angles relate to the arc length of a circle. So if we're traveling around the circumference, what does it mean when we measure different angles? So we have historically, up to this point in your math career, measured angles in degrees. Right? And so we know that there are 360 degrees in a circle, and we can use a protractor to measure them, and that's kind of the realm that we've lived in. Your calculator is probably in a mode that's signified with a little D or DEG written on it, and that's been perfect up to this point. But there is a new unit. It is called a radian. And so a radian is defined as, if we're looking at a circle, and maybe I'm going to draw a circle in here. Bear with me. Hopefully that looks like a circle to you. Okay, so we've got our circle, and we've got our center point here. Well, we know that our radius extends out from the center to the circumference of the circle, and that has some length, r. If we then took a piece of string that was exactly that length, and we tried to shape it to the distance around the circumference, it would look something like this. So we would be able to curve it to follow the circumference. And it's that distance, the angle that's created by that exact piece of string, that is 1 radian. Because it's 1 radius's worth of arc length. So that sounds like a kind of weird idea, and there's a typo in here. We're going to use the letter S to signify arc length, and I know that sounds weird. It's the letter that you're going to see on your provincial formula sheet, so that's why I want to be consistent. And so there is a formula to relate this any arc length of a circle with the angle that we measure based on its radius. So our formula in general is that our arc length is equal to our radius multiplied by the angle. Now, the tricky part here is that angle, I'm going to do this in red just to make sure, must be in radians. And you're like, but it's still a little weird to me. So what happens is that this is actually where the number pi comes from, that 3.14, etc., is equal to going around a circle exactly half. So getting all the way over to here takes exactly pi radiuses. So if I took another string, made it exactly the length of the radius, I would be able to go to here, and then I would take another one, and I would maybe be able to get to here, and so then I'd have a little bit left over, and that would get into my 4th radius worth of string, and thus that's the 3.14, etc. Okay, but we'll always be using pi because, as you may have noticed in the last lesson, we are really loving the exact values, and that is not going to change. That's the majority of the space that we're going to work in for all of grade 12 pre-cal, which is why there is such a big non-calculator section of the provincial exam. So exactly pi radians, 3.14 ... is equal to 180 degrees. And so 360 degrees is equal to 2 pi radians. Now the nice thing about radians is that we don't end up actually writing this word. So when I talk about an angle being pi, like theta equals 2 pi, I don't need to write radians, and it's implied. When I get to writing just the number or the value, if I was writing like 3.14 radians, then I would need to include it. But when I talk about exact value, and even then, not really. If I write theta equals just a number, I'm talking about radians. So these ratios here are what are going to allow you to convert back and forth. So 1 radian is equal to 180 divided by pi, and that's coming from this. And so 1 degree is equal to pi divided by 180. What you always, in terms of converting units, it kind of is helpful if it's always what you have or what you want over, or what you have over what you want. Your known or over your unknown. In terms of converting units, it's always what you end up wanting to have over what you already have, or your unknown over your known. So when I go to this first example, I'm going to be using this ratio because I'm always trying to convert the following from degrees to radians. So I want radians, that's my unknown, so that's in the numerator, pi, and the part of the ratio that goes in the denominator is what I already have, which is degrees. So I'm going to take 255 multiplied by my ratio, pi over 180 degrees. And that allows my units to kind of work against each other. So I'm left with 255 pi over 180. And it says express your answer in terms of pi and in decimal form using the ratio. Okay, so we'll practice both leaving it in exact value form and in terms of using our calculators to convert it. So here you would look for your biggest common denominator. We would maybe say, okay, well, 255 divided by 5 would give me 51. That seems like it might be a prime number. So I'm going to go 51 pi. Actually, I should work downward. Don't put multiple equal signs in a row. 51 pi, and if this is divided by 5, that would be 36. Okay, but 51 actually is divisible by 3, so that would get me 17, and I know 17 is prime, and 36 would give me 12. So this would be my answer in radians. Okay. If I want that in decimals, all I have to do is type in my calculator 17 times pi, and then I'm going to divide that by 12. Gives me 4.4506 radians. Okay, and about that. Again, we want to keep like 4 decimal places at least when you're doing your provincial exam, so it's a good habit to get into right now. So pause the video right now and try the next 3 examples on your own using the exact same method. We're doing the exact same thing, degrees to radians, so you're not even going to have to flip this ratio around. How'd you do? Did you get these answers? Please note that in the video there is a mistake and this should be negative here. If not, please feel free to revisit this, to shoot me an email, to put it in the help section in the collaboration section of our OneNote here. So again, if you're not sure where that is, you would go up here and back to the original page where you can access like the general info and where you've gotten into the course content library, there's also a collaboration space that you'll be able to access. So example 2, convert the following radians to degrees. So again, we're going the opposite direction. We want degrees and we have radians. So instead of setting it up like this, we always put what we want in the numerator, 180, and what we are getting rid of in the denominator so it can cancel out our units. Okay, so again, this would equal degrees over radians. So we'd multiply this by 180 over pi. And all of a sudden, pi cancels out and the radians go away because we've got radians down here. And degrees are left over. So we're left with 180 degrees divided by 7. And so it says just to write our answer in decimal form. And so I just need to punch this into my calculator, 180 divided by 7. And that gives me 25. And again, we want to keep 4 decimal places at least. So 7,143 degrees. That would be my answer. So in some ways, converting back to degrees is a little bit easier because we don't need to mess around with that whole exact value thing. If you want to try and give these 3 a shot, pause the video now, try it on your own using the exact same method. Always remember what we want or what we're working towards divided by what we already have, what we're trying to get rid of for that ratio. Okay, so again, you can check your answers with these ones, make sure that they make sense, and let me know if any of the work that I've shown here is a little confusing. In terms of this first one, I was just, again, canceling out pi's. I also looked to reduce because I know that 9 goes into 180 evenly. So that's what's going on there with all those extra strokes. So that's all dealing with converting. And once we can convert to radians, now we can start talking about arc length. So all arcs that subtend a given angle have the same central angle. So they're still touching the origin if we're working on a Cartesian plane, but they have a different arc length depending on the radius. Okay, so the arc length is proportional to the radius because a bigger radius means a bigger circle, so it's just going to cover more distance for the same degree. And that kind of fits with the whole definition of a radian, because a radian in this smaller circle is only going to be this long going around the circle, whereas in our larger circle, we're going to use this radius, a much bigger length, as the measure of 1 radian. So it kind of makes sense as to why a bigger circle with a bigger radius also has a bigger arc length for the same angle. So again, this formula is the one we're going to use. S stands for arc length. Theta has to be measured in radians, and R is our radius. So for example 1, we're given the radius, we are given our angle already in radians, so good news, this is in radians. We're asked for the arc length. So we simply plug and chug 9.2 times pi over 5. Now, we're not specifically told we want exact values, so here would be a perfectly good example of where you can give a decimal for an answer. And when I punch this into my calculator, I get 5.7805. In our second part of the example, unfortunately, it is in degrees, so we're going to add that extra step of having to convert to radians first. So again, we have degrees, So we've got 115 degrees. I want radians, so I'm going to put them in the numerator, and I already have degrees, so I need to be able to cancel them out, so they need to go in the denominator. And that's how I set up my ratio. From here, I can leave it in exact value, or I could convert this immediately to a decimal, but again, exact value just lets you be a little bit more accurate. So dividing both of these by 5 gets me 23 pi over 36 radians, in which case I am able to use our formula. So it's not a bad idea when you're using a formula to write it down before you actually start plugging in, strictly for the purpose of helping it kind of stick in your brain and become familiar, so that that formula is associated with the math that you're doing, so that you don't have to think quite as hard about making those connections, because it's already kind of trained into your brain. So if we go, our radius is 4.8 and our theta is 23 pi divided by 36. Then when I punch this into my calculator, I will get my value of my arc length, which is 9.6342. Because my radius doesn't have any units, neither will my arc length. So if you want to give C a shot, it should follow the same pattern as B. Okay, so you'll notice that my solution is positive in this particular example, and that's because it doesn't actually matter the direction that my angle goes in terms of just measuring length. Length doesn't have direction associated to it, so my arc length isn't ever going to be negative, so I don't need to use the negative when it comes to my angle. But I kept it in with my theta because the value of the angle itself is still negative. So that's why that kind of changed there. Our last one is looking for our angle. So we're going to have to manipulate our formula a little bit. So instead of S equals R theta, we're going to have to move that R by dividing. And so we're going to get theta equals our arc length divided by our radius. Given the fact that we already have both of these values and they don't have specific units that they need to be as long as they are the same, we have 235 divided by 5.8, and that gets me 235 divided by 40.5172. And that should be in radians. And there we go. So that's our final answer, and that is our last example. So I'll be posting a worksheet to go along with this in terms of conversions and also applying this arc length formula. So you'll want to give those a shot. And I'm thinking that our first assignment that's going to show up on Quest is going to look at both just our standard position angles and what we've covered in this lesson, specifically because when we get to lesson 3, we're going to start looking at radian measures and kind of where they fall. So those will show up as well, and that'll be the third lesson that shows up in that assignment. So it'll be posted about the middle of next week. But good luck with your homework for our current lesson that we just finished, lesson number 2. And if you have any questions, please reach out.